Creating a program that runs on a quantum computer is actually not that hard to do. So I wanted to walk through a little Hello World example of creating your first quantum computing program that will output Hello World based upon a random number. So generating random numbers in a quantum computer is probably one of the most basic things to do. I am here in the IBM Quantum Composer, and this is free. You can access this yourself if you just search for it and access the composer. Now, I will be showing this in Python code in just a second. We're going to actually write a program that runs on a quantum computer. But before we do that, I just wanted to show you the simulator to give you an idea. So I have up here a very simple circuit. It contains one qubit. By the way, a qubit can hold the value of 0 and 1 at the same time, or a value in between. That's called superposition, and that is the magic behind quantum computing. So where a classical computer bit is 0 or 1 at any instance, like a light switch on or off, a quantum computing qubit holds the value of 0 and 1 at the same time, almost like that light switch is both off and on at the same time. And this is where the magic happens. So when we start, I have one qubit and one classic bit. We need the classic bit in order to measure the qubit. So when we start out, you can see right here, the value is 0, right? The value is 0 that we're measuring in the classical computational basis state. If you want to flip that to a 1, you can just put in a not command on that qubit. And now that 0 will always become a 1. So 100% of the time, if you measure this qubit, it's going to measure 1. If we take off that inverse gate or X gate, 100% of the time, it's going to measure 0. Okay, so that's not really very fun. We've only just mirrored a classical bit where we can have 0 or we can have 1. That's not what we're going for here. What we want to see is a random number. We want to see this be 50% 0 and 50% 1. The way we can do that is to place that qubit into superposition. We use a Hadamard gate, and look what's happened. Now that qubit is measuring 50% of the time 0 and 50% of the time 1 in one measurement. So what we have here is a qubit that is measuring both 0 and 1 at the same time. If we want to be precise about this, we can add a measurement command onto the classical level, and now you can see this is a correct circuit that will return a random value of 0 or 1 50% of the time. Okay, so let's jump over to the Python code now that you've seen this. And I want to show you how you can program this. So the first thing to do is I have a Python Jupyter notebook up here. You can do this in an executable. You can do it in a notebook. I only chose a notebook because I want to be able to show some visualizations. So the first thing you'll need to do is pip install Qiskit and pip install Qiskit AER. AER is just the quantum computing simulator that we're going to use in order to run this on my computer. You can actually send this to the real quantum computer at IBM that IBM Composer is using. If you want to, you can use your API key and run it on their actual machine. I'm just going to run it in the simulator for now, and that's good enough for me. So I've imported the libraries. And now I want to show you a baseline. So let's generate some random numbers in Python. This is just using the Python random module. There's nothing magical happening here. We're just going to generate a random number between 0 and 1, and we're going to collect the results, and then we're going to plot a histogram. So let's just run that. Okay, that ran pretty fast. If we take a look at the numbers and plot a histogram, what should we expect? Well, we should expect 1 and 0 to appear 50% of the time. That looks pretty random, right? If we look at the histogram, you can see here 55 times we got a 0 and 45 times we got a 1. That's pretty good. If we increase the number from 100 to, say, 1,000, we'll probably get closer to 50-50. Let's run that again. Let's see if we get closer to 50-50. Yeah, see that? So we got 500 zeros and 500 ones. That's That's pretty impressive. I'm just curious if we run that one more time. Yeah, see, that's a little bit more likely. 529 times, we got a 0. 471 times, we got a 1. So that's a random number, right? Let's put that back to 100, just to be precise here. Okay, so we can see here we can generate random numbers in Python. Nothing new. What about on a quantum computer? So we saw the simulator, how we did that. Now here's how we do that in Python. We use Qiskit to create a quantum circuit with 1 qubit and 1 classical bit, just like we saw in the composer, okay? In case you've forgotten, this is what it looks like. We have 1 qubit at the top and 1 classical bit, which we'll be measuring that qubit into. And we want to get back 50%, 50% zeros and ones, right? So back in the code, you can see here, we've created that quantum circuit, just like we did in the composer. We're going to create a simulator just to run it so we don't have to run it on a physical quantum computer. Although you can use IBM's quantum computers to run this. They're free. You can call their API using your API key. And then what we're going to do is we're going to add onto that circuit the Hadamard gate to place that qubit into superposition. That will make that qubit register not just a 0 and not just a 1, but it will be 0 and 1. And then we can measure it. And then we can see the output. So let me show you what the circuit looks like. This draw command will draw the circuit for us. So if we run this, take a look at that. This looks just like what we saw on the dashboard, right? In case you need your memory refreshed here, we'll refresh our memory. There's that Hadamard gate that places the qubit into superposition, and there's the measurement. So back in our code, you can see here we have the same exact structure. There's our qubit, and there's our classical bit that we're measuring it. So what we expect to get back is 0 50% of the time and 1 50% of the time. So we're going to run this. We're going to run this 100 times just like we did before with the Python random number. We're going to compile our circuit, okay? We're going to run the circuit. We're going to get back the results, and we're going to count them. We're going to get the counts of zeros and the counts of ones for that one measurement. We're going to take the max, either 0 or 1, the max times. Remember, we saw 500. We go back up here. We saw 0 appear 529 times and 1 appear 471 times. We're going to take the max, which will be a 0, and that will be our random value. So that's what we're doing here. And then we're just going to count up the occurrences. So actually, I don't think we need, this will probably run faster if we compile that circuit beforehand. All right, let's run that. So you can see here in the output, we have 0 502 times and 1 522 times. That looks just like our Python random code, doesn't it? But now it's running on a quantum computer. Well, technically a simulator of a quantum computer, but that's still pretty close. If we plot a histogram of that, of course, this is what we're going to see. So you can see here 61 times. So we are going through a count of 100. So out of 100, oh, by the way, the print here, the reason the numbers are 500 is we're printing the counts, not necessarily the results. We can print the results too if we were to do that. Maybe you want to see the results before the histogram. We can add that too. So there you go. 59 times you got a 0, 41 times you got a 1. That's pretty random. This is just one instance. This is all of them running the loop. So we take a look at that histogram. This looks pretty random. This is what's coming back from the quantum computing program. We got 39 zeros, 61 ones. That's pretty random. Let's run it one more time. Okay. Take a look at that histogram. That's a lot closer. 49 times we got a 0, 51 times we got a 1. That seems pretty random. And that's from a quantum computer. That's from a quantum computing program. So here's where things get cool. Let's package this into a little program we can use, and we're going to make it show hello world. So all I've done here is I've created a function called create circuit that just returns that quantum computing circuit with 1 qubit and 1 classical bit. We place that qubit into superposition and we measure it. I've also created a function called getRandom, which measures the result. It executes that circuit, it executes the quantum computing program, it gets back the result, counts them, and gives us the max of that count. Returns that as an integer, which will be 0 or 1. We'll just load those functions. And now I'm going to create a method called sayHello. All this does is, number one, it creates the circuit, and then it calls getRandom. If it's a 0, we'll show hello world with a frowning face. If it's a 1, we'll show hello world with a happy face. So let's run this and let's see what we get. Okay, so you can see that the quantum computing program got back a 1, which means the happy face that you see here. Now what if we run it again? Another happy face, another happy face. One of these times it's going to be a frown face. There we go. Okay. Fourth, fifth time's the charm. So this time it got back a 0. So it shows hello world with a frown face. Let's run it a couple more times and watch the face change as we run it. You can see it toggle between happy and sad according to what the quantum computing program is measuring on that qubit of 0 or 1, or I should say 0 and 1. So I want to show one more thing that really brings this home. Can we do this with an image? Well, yes, we can. Here is meow or ruff or woof, depending on how you like to say the dog sound, a bark. Maybe that's what it should say. We create the circuit, the quantum computing program. We'll get back that random number from the quantum computing program by measuring that qubit. And then if the qubit is a 0, we'll display a cat. And if it's a 1, we'll display a dog. So let's run this and see what we get. Okay, that one was a cat. Let's run it again. Another cat. And now I get a dog. So that time it was a 1. So you can see as we run this, the quantum computing program is executing it each time. And it's getting back either a 0 or a 1 and displaying the image as it changes between a cat or dog. Well, that's a lot of dogs that time. So various factors can influence the randomness of the qubit. These include electromagnetic fields, temperature differences, random noise fluctuations, electron tunneling, all of these things that are part of the quantum computing world and effects that occur at the microscopic level compared to the macroscopic world. So you can see here we have successfully implemented a random computing program that uses quantum computing to generate a random number that is displaying an image based upon that quantum computer. And we could, of course, execute this directly on IBM's physical quantum computers using our API key if we want to, or you can run it in the simulator just like this. So I hope that you really enjoyed this video. I certainly enjoyed putting this together. I am very passionate about quantum computing, and if you'd like to learn more about this, leave me a comment, subscribe, like the video, and maybe I'll make more of these and go into a bit more detail on what we can do with quantum computers.